So, hello everyone. My name is Han, and I am the guided study group leaders for Math 140 this semester. So this is my third semester working with Dr. Kasher, and in these sessions, what I'm gonna do is that I'm gonna quickly go over the materials. Maybe sometimes I go a little bit too detailed about the lectures. It's just because I want to make sure that I cover all of the points that you guys wouldn't miss. And then I will go over some representative problems that you guys might run into, especially for that part of materials, and kind of like better prepare you for the exam and kind of like understand the material a little bit better. And so, for those who joined me earlier today from 6 to 7 p.m., again, I'm really apologize for the internet connections and because I'm currently not in the US and I'm in Vietnam, which is like 12 hours away and half an hour away from State College, and the internet connection was not that good, and plus there's a storm this morning. So again, I really apologize for that. And so now I'm recording this session so that you guys can listen to it, and especially for those who couldn't make it to the time that I selected, you will still be able to catch up with what we are doing. And so today I'm going to go over session 1.8, 2.1, and 2.2, which is continuity and then the definition of derivative as at a point and as a function generally. So this is section 1.8. So let me go to that slide. So 1.8 is continuity. So a function f is continuous at a point x equal a if you have limit of x approaching a of fx is equal to fa, which is kind of like give you a general impression of a graph which is continuous, mean that you have like a smooth curve and you have a point there where you have the limit of x approaching a on both sides is exactly the value of that function at that point, which is kind of like say you have a smooth curve because there's nothing that's not equal, like not there's no limit to a point that is not equal to the value itself. Now to get that condition satisfied, basically you need to satisfy three conditions to get continuity, which is you need fa, so the value of the function at that point have to exist. Then you need limit of x approaching a of fx exists, and you need those two to equal to one another. However, for piecewise function, where you have a function that is defined by more than one expression, then you have to find the limit of x approaching a plus of fx, and then you have to find limit of x approaching a minus of fx, and you make sure that those equal to one another and equal to f of a. And I'll go deeper into this when I go into the example. And then you have a part of continuous on the left and on the right, which is kind of like just replace this last condition by, so on the left, you have, this is the point, and then you go through that. You go to that point, mistake of that drawing, but kind of like I try to make a smooth curve. So what you're doing is that you're just gonna take the limit of x approaching a minus of fx, and you make sure that it equal to fa. Of course, this limit have to exist for that to happen, and you have the right. It's kind of like a similar thing. Instead of a minus, you have a plus. So limit of x approaching a plus of fx equal to fa. Again, you have to make sure that this limit has to exist before you can do anything about the equality. And so you're also introduced to some discontinuity. And I think this is not a very important part, but it's really good to know, especially when you're given a problem. I think in chapter 3, when you start to have to graph something, and they give you something like you have a removable discontinuity or a term discontinuity or an infinite discontinuity, then you should be able to understand the terminology and how it can be translated into mathematical expression. And so a removable discontinuity is basically look like this on the graph. So so kind of like you have a curve which is smooth everywhere except for at a point, and the value at that point actually lies somewhere else. So in math or in calculus, it can be translated into the fact that you have limit x approaching limit of x approaching a of fx is not equal to fa itself. So you have these two conditions satisfying. The first two conditions in those three satisfy, but the last one is not. Then you have a jump discontinuity, which can be translated on the graph as something like this. As easy as that, where you have a range of a point it can be, and it's kind of like get a jump over there. So what happened in this case is that you can be translated into limit of x approaching a minus of fx. It's different from limit of x approaching a plus of fx, and also different from fa itself. It usually is the case, but you have to look at how the graph look like and maybe what the problem specifies for you to make sure if those three are satisfied, those three conditions of differences exist at the same time or not. And then finally, you have infinite discontinuity, which is kind of like if you have learned something like this in high school, you'll be able to know which is vertical asymptote. But if you don't remember, what happened is that on a graph, it's gonna look like this. When you have, say, a straight line, say this one is x equal 1. What happened is your graph is gonna approach infinity, approach y equal infinity when it approached this line. So it's kind of, I'm not gonna go too deep into this, but we're gonna continue talking about this when you get to chapter 3, where you learn about how to especially graph a function and like some asymptotes about it, vertical, horizontal, and maybe even diagonal asymptotes, line asymptote. That's how I call it. And then in 1.8, we also have a theorem, which this is like it's saying if you have f and g are continuous, I'm gonna say CTS is continuous as x equal a, then you have these function f plus or minus g, f c times f, so it's a scalar multiple of a function, and then you have f times g, a product of two functions, and f over g, which g at a is different from 0, so kind of like keep the function defined, so that this fraction is meaningful, and so those functions are also continuous at x equal a. So this is what the theorem is saying. Now, kind of like as a list, kind of like listing out for you, we have these functions that will always be continuous on their domain, which is polynomial, kind of like really familiar with you. It's kind of like in the form axn plus bx to the n minus 1 plus until you have c, which is like a constant, and then you have rational function. Now that's why I'm saying on their domain, because rational function is usually in the form of px divided by qx. Now you need the denominator to be different from 0 so that the fraction is meaningful. So that's why the domain will exclude the point that is not the denominator is 0 or the fraction is not defined. So the rational function is continuous on its domain. And then we have the root function, so which is like maybe the nth root of px. So what you have to be careful here is that it's not that important for our root, because You don't need the expression inside the root to be positive. But for the expression inside an even root, say square root or like maybe the fourth root, then you need the expression to be positive. And so that's why I'm saying it's continuous on its domain. And then you have trigonometric. Usually if you have cosine x or sine 2x, those simple things, then it wouldn't be really of a problem. But when you see something as odd as cosine of 2 over x, then you have to be careful about this part of fraction where 2 over x is not defined because x can be 0. And finally, we have a very important theorem called intermediate value theorem, where you can use this to solve I think one of the biggest application of this theorem is that it allows you to prove, say, your function cross some line at least a point in an interval. So the theorem is basically saying, suppose f is continuous on a closed interval from a to b, with fa smaller than n smaller than f of b, kind of where fa is different than fb. So I'm kind of like giving this as a function. So this is f of b, and this is f of a. What the theorem is saying is that you're gonna have a line of n in between these two values, so that you have at least one point. If you have a continuous function,